Solving polynomial inequalities. One application of our ability to find intercepts and sketch a graph of polynomials is the ability to solve polynomial inequalities. It is a very common question to ask when a function will be positive and negative. We can solve polynomial inequalities by either utilizing the graph or by using test values. Example 5. Solve x plus 3 multiplied by x plus 1 squared multiplied by x minus 4 greater than 0. As with all inequalities, we start by solving the equality x plus 3 multiplied by x plus 1 squared multiplied by x minus 4 equals 0, which has solutions at x equals negative 3, negative 1, and 4. We know the function can only change from positive to negative at these values, so these divide the inputs into 4 intervals. We could choose a test value in each interval and evaluate the function f of x equals x plus 3 multiplied by x plus 1 squared multiplied by x minus 4 at each test value to determine if the function is positive or negative in that interval. From our test values, we can determine this function is positive when x is less than negative 3 or x greater than 4, or in interval notation, negative infinity, negative 3, union 4, infinity. We could have also determined on which intervals the function was positive by sketching a graph of the function. We will illustrate that technique in the next example. Example 6. Find the domain of the function v of t equals square root of 6 minus 5t minus t squared. A square root is only defined when the quantity we are taking the square root of, the quantity inside the square root, is 0 or greater. Thus, the domain of this function will be when 6 minus 5t minus t squared is greater than or equal to 0. We start by solving the equality 6 minus 5t minus t squared equals 0. While we could use the quadratic formula, this equation factors nicely to 6 plus t multiplied by 1 minus t equals 0, giving the horizontal intercepts t equals 1 and t equals negative 6. Sketching a graph of this quadratic will allow us to determine when it is positive. From the graph, we can see this function is positive for inputs between the intercepts. So 6 minus 5t minus t squared greater than or equal to 0 for negative 6 less than or equal to t less than or equal to 1, and this will be the domain of the v of t function. Writing equations using intercepts. Since a polynomial function written in factored form will have a horizontal intercept where each factor is equal to 0, we can form a function that will pass through a set of horizontal intercepts by introducing a corresponding set of factors. Factored form of polynomials. If a polynomial has horizontal intercepts at x equals x sub 1, x sub 2, and so on, x sub n, then the polynomial can be written in the factored form. F of x equals a multiplied by x minus x sub 1 to the p sub 1 power multiplied by x minus x sub 2 to the p sub 2 power, and so on, x minus x sub n to the p sub n power, where the powers p sub I on each factor can be determined by the behavior of the graph at the corresponding intercept, and the stretch factor a can be determined given a value of the function other than the horizontal intercept. Estimating extrema. With quadratics, we were able to algebraically find the maximum or minimum value of the function by finding the vertex. For general polynomials, finding these turning points is not possible without more advanced techniques from calculus. Even then, finding where extrema occur can still be algebraically challenging. For now, we will estimate the locations of turning points using technology to generate a graph. Example 8. An open top box is to be constructed by cutting out squares from each corner of the 14 centimeter by 20 centimeter sheet of plastic, then folding up the sides. Find the size of squares that should be cut out to maximize the volume enclosed by the box. We will start this problem by drawing a picture, labeling the width of the cutout squares with the variable W. Notice that after a square is cut out from each end, it leaves a 14 minus 2W centimeter by 120 minus 2W centimeter rectangle for the base of the box, and the box will be W centimeters tall. This gives the volume V of W equals 14 minus 2W multiplied by 20 minus 2W multiplied by W equals 280W minus 68W squared plus 4W cubed. Using technology to sketch a graph allows us to estimate the maximum value for the volume, restricted to reasonable values for W, values from 0 to 7. From this graph, we can estimate the maximum value is around 340 and occurs when the squares are about 2.75 centimeters squared. To improve this estimate, we could use advanced features of our technology, if available, or simply change our window to zoom in on our graph. Try it now. Use technology to find the maximum and minimum values on the interval -1, 4 of the function f of x equals -0.2 multiplied by x minus 2 cubed multiplied by x plus 1 squared multiplied by x minus 4.